Today.
This call is now being recorded.
So, first of all, in quantum physics, we need to remember that there are two theories. There are basically one old theory and there is a new one. So, first of all, we are going to put a splitter here and then learn what is the difference, okay, between these two. So, wave theory is a old concept, and in wave theory, you guys need to remember that. Okay. So in wave theory, it is believed that electrons can be emitted from any source as long as light is incident onto it. Okay. So then it says that the light has a continuous nature which is accumulated by electrons till they have enough energy to release. Right, so this is basically the wave theory. Wave theory means that energy from light can be accumulated slowly, and then obviously it can be released like that. But photoelectric effect has a different opinion about it, completely different. Okay, so first of all, we're gonna learn about basically what uh, is the reality of how light is made up and how things absorb it. So in photoelectric effect, it says light has a particle nature. It is not continuous. It contains, so I'm just writing in very simple terms, it contains small, indivisible. Indivisible means you cannot further, reduce them. Discrete particles called quantums. All right. Now, quantums and photons. Photons is basically the later on we used it, right? So now, what is the basic conflict here? The conflict is huge, actually. The conflict is that it says that only when a light of certain frequency is shown onto a metal plate, then electrons are ejected. Okay, so first of all, we need to understand, all right, that not any source, like as long as light, it says, wave theory says, as long as any light is shown, electrons can be ejected. But quantum theory says that only when a specific frequency, like a certain frequency and above, is shown, then it can release electron. Then it says that even faintest faintest or dimmest light, like UV is the minimum that can, do that, causes electrons to be released. All right. And brightest visible light cannot release electrons. So it's just not like you can do it with any wave. You have to have a particular wave. All right. Is it clear, everyone? Now, then it is believed that intensity of light increases intensity of light increases the number of electrons released per unit time. All right. It does not increase their maximum kinetic energy. All right. Wait a second, please. Okay. Now I'm going to explain this in a bit. I just want to, make a longer line now. Sorry about that, because there's certain points that cannot be missed. Okay, like this. All right. Then it just says that. Yeah. Sorry.
Could you read the point that says even something or dimmest light? What does that say?
Faintest or dimmest.
All right.
Okay. All right. Then I have to write the next thing, which says that. So it says there is 1-to-1 absorption. There is 1-to-1 absorption of photon by an electron. Okay. So it cannot be shared, cannot be accumulated, or shared. You guys need to understand that. Now, so then I just want to tell you that if the photon has equal or greater energy than work function of a metal. So we're going to talk about work function in a bit as well. Only then electrons are released. All right. And we just need to remember one thing, that work function depends on the threshold frequency of metal. So I'm gonna explain this to you in a bit. Just write it down, please. Everything. Take your time. I'll be back in like 2 minutes. Yes. If you have something you
Last,
want to. Sorry.
could you zoom into the last points?
Yeah. Here. Is it okay?
Yeah, sir. Thank you.
All right. Just write it down, and then I'll be back in like 1 minute. All right then. So let's go. Okay. So
Sir, could you scroll up?
yes, please here.
No, to the top.
Okay, to top like that. Okay. Now, so the reality of all this is that what we're really looking at is right now. Let's right here. So what we're saying is that actually there is a metal, okay, like this, and when light basically is incident on it of a frequency, let's suppose f, all right. So the metal has its own like threshold frequency f naught, okay. And if this f is greater than f naught, only then electrons are released. So not all lights can do that. It's minimum ultraviolet can do that, and then lights above that as well. Now, that means that it's not like you can keep on, accumulating energy, and when you have enough, you can release the electrons. That's not how it's going to be. So, you guys have written. Should I go to the next one, please?
Just a second.
Not done, sir.
So what do you mean by it does not increase the maximum kinetic energy?
Yes, I'm going to explain that to you. So, you guys should understand that the law of conservation of energy, okay? I'm going to write it like here. Law of conservation of energy. The law of conservation of energy means that you cannot, destroy or create energy. Energy needs to be conserved, okay? What it means is that if you have the energy that comes from light, so that's energy of photon, right? And if you subtract it with the work function is the energy required by a metal, right? The difference of these two is going to give you the remaining energy. So the remaining energy is converted to maximum kinetic energy that the electron will have, all right, when it is released. Is it clear? Like that. Now should I go forward?
Yes, sir. Could you just scroll a bit down, please?
Yeah.
Yes, thank you.
All right. Very good. So then we're gonna go to the next slide. Should I go to the next slide, please, everyone?
Yes.
Okay. So, all right, now it says you need to write the 3 pieces of evidence that you see from this, right? Now, the first piece of evidence is that only when ultraviolet light is shed, so then only electrons are released. Do you guys understand this? Then the next piece of evidence is that only if you increase the intensity, the rate of electrons release increases. It does not increase the maximum kinetic energy, which means the electrons don't go faster. It's just that more electrons can come out now. Okay, let me just write it down for you because I think you guys won't be able to. Yeah, I want you to get this part correct in any case. All right, so we can say that only when ultraviolet light is shown onto metal, electrons are released. All right. So intensity affects the rate of emission of electrons, not their maximum kinetic energy. So you can write that. And faintest or dimmest ultraviolet can release the electrons instantly, right? So there's no accumulation, you can write that too. All right, anyone who doesn't understand this, please let me know. All right,
So
now
what's
isn't
the
the
last
first
point?
one and third one the same thing?
first one and third one. No, first one basically talks about the frequency, and this one talks about instantaneous release of electrons, even if the intensity is low. Do you understand?
Yes, sir.
Okay. Now, before we come
Sir, could
back,
you explain the third one?
yes, what I'm saying is that if, let's suppose, there's a metal and there's an electron and a photon comes, which is like of a required frequency, the electron will be instantly released. Even if the light intensity is very low, like it's a very dark room and there's very little light, still electrons will be released if they get the required frequency photon. Is that clear?
All right. What have you written, by the way?
The interest to diminish UV can release the electron instantly.
Sorry?
The interest to diminish UV can release the electron
Oh,
instantly. Okay.
okay, sir. Okay, okay.
What
Thank
is
you.
written in the bracket though?
Instantaneous release of electrons.
Okay.
Even if you write what's written in the bracket, then it's all right. It's also okay. Okay. You can also write that visible light, no matter how bright or how intense it was shown onto the plate, it could not release any electrons. You can also write that. Okay, done? All right. Now, how do we find the energy of photon? Because we're talking about the energy, frequency. We don't know that. So we need to understand this, that energy of photon is given by Planck constant times the frequency of the wave. All right, we can say whatever light we're looking at. So it is given by E is equal to HF, all right, like that. Alternatively, because the speed of light is also equal to F lambda. So F will be equal to C upon lambda, right? So we can replace that. So we can also write HC upon lambda. Will you guys be able to remember this? Both formulas? So in this particular question, it says that there is each metal is irradiated with an electromagnetic radiation of 380 nanometer of light. Okay, that's the wavelength. And they have given the work function as well. Okay, now they say calculate the energy in eV of photon of radiation of wavelength 380. So we're gonna say H is 6.63 times 10 raised to power minus 34. That is the same thing. The speed of light is 3.0 times 10 raised to 8. And the lambda is 380 into 10 raised to power minus 9. Okay. Can you guys please find the answer in joules?
(5.23 times 10 raised to negative 19).
All right. Now we got to change it into EV because they want us to find an EV. So 1 electron volt is given by 1.6 times 10 raised to minus 19 joules. So how many electron volts will be in 5.23 times 10 raised to minus 19 joules? You can cross multiply or you can simply divide the larger value. like this. What you get? I think it should be 3 something. I think 4 maybe.
3.3.
3.3 electron volt. Is that clear, everyone? Any questions? Now, this is the energy of each photon that is shown onto this onto these plates, all right, onto these metals. It says determine which metals will give rise to emission of photoelectron. Explain your answer. Now, this is the energy we have, and these energy basically are the required work function, means required energy of a metal to release electrons. So what do you guys think, which metals will do that?
Sodium and calcium.
Yes, it will be only sodium and calcium. And the reason why these will do it, because the photon energy that we just found out is greater than work function. Is it clear, everyone? Or energy required by the metal? Any questions, please let me know. It's easy, right? Would you be able to do it in the exam? Okay. Now, in the next part, say the photons of wavelength 380 are incident normally on the metal surface at the rate of this. So they've given you the amount of photons that are incident. All photons are absorbed in the metal surface. No photoelectrons are emitted. Calculate the force exerted on the metal surface by incident photons. Now, no, we're going to do this much later, okay? In fact, I'll give you this homework when we cover the Brod's wavelength today. Anyway, so going towards the definition of a photon, which is obviously very, very important. So the photon definition is, you can write the energy contained within a photon is proportional to the frequency of light it belongs to. Okay, so basically it's just the same formula. E is equal to HF, where E is the energy of photon and H is the Planck constant. Planck constant is given, by the way, and F is the frequency of light, whatever light it is. Anyway, then it says what is threshold frequency. So to define threshold frequency, we could write that it is unique frequency of light required by the metal to eject electrons from it. Okay, you can also write remove electrons. The symbol we use for threshold frequency is F naught, and because it's just frequency, so SI units will be hertz. It's correct. Now, obviously, like I said, threshold frequency is equal to, like, it depends on work function, and work function is the minimum amount of energy required by incident electromagnetic radiation to a surface to remove electrons from the metal. Now, obviously, work function, the symbol of work function is like pi, like this, and work function is equal to Planck constant times the threshold frequency. So the max kinetic energy would be, basically, when you want to find this, it's pretty simple. We just need to use the math behind it. We're going to say, so we're getting energy of photon, okay, minus work function, and that is giving us whatever extra is left, like I told you, goes to kinetic energy max. So it means kinetic energy then can be written as energy of photon is hf minus the work function is hf naught, like this. So that means that then I can basically compare this with y equals to mx plus c. So I have kinetic energy on maximum kinetic energy, right? On the y-axis, as you can see, the frequency on the x-axis, as you can see, which means that the graph will have two things. The gradient of this graph is going to be Planck constant, h. He may ask you to find it as well. And the y-intercept of the graph is going to be negative hf naught, which is basically work function. Okay, so it means that if I draw a line, it will be a straight line with the negative y-intercept. This point is the work function, and that is hf naught, as you can see. This point will be f naught, which is the threshold frequency. As you can see, at threshold frequency, the kinetic energy will be 0. It means electrons will be just released with no kinetic energy. And after that, whatever increase in energy is, whatever the frequency after threshold frequency is, that's when the electrons are going to keep on releasing. And that's why the line will be in the positive gradient. If you find the gradient of this line, like this, so the gradient of this line will give you h, which is Planck constant. Any questions, please let me know. You may also draw this, please.
Sir,
Yes.
so why does the emission not start from the work function?
It does start from the work function. It's just that what it means is that work function is basically the energy required. It means this much energy, Kartika, is required for it to start the emission. Do you understand?
Okay, yeah.
Okay. All right. Any other question you
So
guys
the
have?
emission will start beyond threshold frequency, right?
Yes. That's when you see it has kinetic energy maximum, right? Okay. Should I go forward? All right. So then you have this sort of question. It says briefly explain the phenomena associated with photoelectric effect that cannot be explained using a wave theory of light. Okay. So now this is an anti-question of how you're gonna explain wave theory. So you just need to write differences. Like for example, in wave theory, light, all frequencies of light can eject electrons. Do you guys understand that? Right? That's what we've learned. Oh my goodness, what did I do? Oh my, wait a second, please. I messed it up. Okay. Yeah. So it can release any sort of, as you can see, any frequency of light, and intensity would basically cause it to accumulate more energy. Or you could also write that basically energy is accumulated, whereas the once it has electrons have enough energy, only then they can release. Okay, but in work function, but in photoelectric effect, the electrons are released instantly as long as they're getting a photon of frequency greater than the threshold frequency. Okay, everyone, do you guys understand this?
At first, there is a 1-to-1 ratio, and then giving more frequency cause it to in kinetic energy, right? For the electrons.
I did not get your question. Come again, please.
Like in wave theory, at first there is a 1-to-1 ratio. Like if we give a certain amount of energy, then it would move just a certain amount of electrons.
No, you're not getting the point. Wave theory doesn't believe that light does not, like, it believes the light is a continuous nature. It does not have a particulate nature. Do you understand?
Yes, sir.
So it says that energy can be accumulated, but according to photoelectric effect, energy cannot be accumulated. It is when a certain energy photon is acquired when an electron, that's when it can be released. Is it clear? So we can write two things. Okay. Number one, frequency below threshold cannot release electrons. Do you understand? Maximum kinetic energy depends on frequency of incident radiation. You can also write that there is instantaneous release of electron. It does not accumulate energy. Is it clear? You get it?
Yes, sir.
Now, this formula you might not have seen this yet because I've not taught you this. Well, I have, but it's all right. This formula basically comes up when you multiply this, you'll realize that it's kinetic energy maximum, it's hc over lambda equal minus hc over lambda naught. So basically, this is nothing but the same formula as hf minus hf naught, because f is c over lambda. That's why they've just given it to you. Now, if they say, what does this mean? So instead of now frequency, we'll just write that it is threshold wavelength. Is it clear? Do you understand? So,
Sir, could you move up a second?
yes.
So what's the second last word in the second point?
Maximum kinetic energy depends on frequency of incident radiation.
Okay.
Okay. Is it clear?
Yes, sir.
All right. Now, if the graph is given, now the graph that we studied, sorry,
Yes. Thank you.
sorry. Okay. Hmm. Okay, so you guys have a break in the like in next 10 days, like from school? Who's
Yes,
still
sir.
No, sir, I have mocks.
oh no, in Ramadan as well.
Yeah, starting of Ramadan and then like 2 weeks, and then I'll be done with mocks.
2 weeks within Ramadan as well.
Yes, sir.
So
Are
last
you?
year when I was having school, we had it the entirety of Ramadan. We didn't get a day off.
Oh no, that's not fair. I was thinking
Exactly.
that I could take your classes daily from now on in the morning. That's fine.
In the morning,
Yeah,
but that won't be possible.
yeah. You
So
see here,
it could be after Isha maybe.
after Isha,
Yeah, it could be. It's better.
it could be, but it's not better for me because after I break my fast, I feel like sleeping only. Anyway, let's go on. Now we're gonna talk about this graph. Now this graph and this graph, please do not mix them up. They're quite different. I tell you why. Because in this one, you have 1 upon lambda, 10 raised to the 6. So it says determine the magnitude of lambda naught. But the whole principle behind it stays the same. So you're going to use your ruler, put a straight line, like extend this line. I don't know how I will extend this because my software doesn't really help me. But anyway, where it crosses like there's no release of electron, that would mean this is equal to 1 upon lambda naught. Okay, just remember that. Not lambda naught, please. So that means this is going to be like 2.1, 2.2. So 2.2 times 10 raised to the 6 equals to 1 upon lambda naught. Can you find lambda naught, please? Yes.
4.5 times 10 raised to minus 7.
Minus 7. So that would be the wavelength. Okay. Now, it says use the gradient to determine the value of Planck constant. Now, we know that gradient is related to Planck constant, but with respect to this, I don't really know. So what I'm going to do is, I know that energy is equal to hc over lambda. We have like if you see, and it's going to be hc over lambda right here minus hc over lambda naught because that's what we have learned, right? Now the problem is that if we find the gradient of this, then the gradient, like it's basically equal to y equals to mx plus c, right? So in this, you guys need to understand this, that in this, the gradient is not equal to the Planck constant, but it is equal to h times c, which is the speed of light times Planck constant, because they're given with respect to wavelength, not frequency this time. So, just take 2 points on the line. So that would be 3 into 10 raised to minus 19, and I think this is going to be 3.6, 3.7. 3.7 into 10 raised to the power 6. Okay, so we got 2 points here. And I'm going to take this point actually. I'm not going to take the point I just took because I just drew the line, because I don't know if that's correct. My line, like, I cannot draw it like on the software. So it's going to be 2.6, 2.7 times 10 raised to the 6 and 1 into 10 raised to minus 19. Okay. Now let's do this. So I'm going to do 3 into 10 raised to minus 19 minus 1 into 10 raised to minus 19 divided by 3.7 times 10 raised to 6 minus 2.7 times 10 raised to 6. Can you please find the gradient for me? Okay, do you guys understand this? What you get?
So it's 2 times 10 raised to minus 25.
Negative
Okay.
5.
Negative 25. Okay. Now it is equal to h and c. So to find h, I got to divide this by 3.0 times 10 raised to power minus 8. Sorry, 8. And what you get?
6.67 times 10 raised to minus 34.
So that would be the estimate, right? Like this. Do not forget this because this is very important and tough question in that sense. Because you can mistake it with the frequency graph. Then says the metal surface becomes oxidized. The photoelectric emission still observed, but the work function energy is increased. Fine. Draw a line to show the variation of this EK max. Now the work function energy is increased. That would mean that it's going to be like somewhere here, like more than before. But the line that they have shown, the line is going to be parallel. The reason why the line has to be parallel is because the gradient is basically equal to h and c, and both are constants. So whether work function increases or decreases or whatever happens, it does not change the gradient. Is it clear? Do you guys understand that?
So can you please repeat?
Like it says, the question says the work function energy is increased. It means the energy required to release photons has increased. So I put it more than what we have found. Is it clear?
Okay.
First of all. Also, I've drawn a parallel line. The reason why I'm drawing a parallel line is because the Planck constant is a constant value, and the speed of light is also a constant value. So the gradient would not change because in this graph, the gradient depends on Planck constant and time speed of light. Okay.
Okay.
Okay, going to the next, all right. The next things are pretty simple. You're going to do it on your own. And I'm going to do towards the experiment to verify Einstein's equation of E equals to h. That's what we're going to do. So, okay. So, this picture is of a photocell. And photocell is like this zinc plate. And there's a light that is incident of certain frequency on the zinc plate, and it is designed skillfully so that when the electrons are released, they are targeted onto the copper rod that we have in front of it. All right. Now, out of the photocell, so this is the photocell here, but out of the photocell, you realize that electrons are going from this zinc plate to this copper rod. So you realize that basically the electrons that are emitted from zinc plate are going in this direction. But what we have done is we have used a variable power supply, and the negative terminal of that power supply, as you can see, is in the direction where the electrons are coming. So the supply electrons are going to oppose this. So there is an opposition going on here, as you can see, right? Now, we keep on changing this. We change this to keep current here 0 because we don't want any current. And what will we get out of this? We're going to learn about this in a bit. All right. Do you guys understand what is happening here at least? So what we're doing is that we need to keep the current in the ammeter 0, okay, or in the circuit in case. And to do that, we use a regulated variable power supply, and thus are able to change amount of work done by battery such that we stop the fastest moving electrons and ensure current is 0. Okay. Now what you guys need to understand is that as you increase or decrease the voltage here, the voltage across the batteries is basically called the stopping voltage, because that voltage is doing work to completely stop the electrons from flowing into the circuit. So it means that the work done by the battery is equal to the maximum kinetic energy of fast moving electrons, and we can use this circuit to find this. Is it clear, everyone? Any questions now? Please let me know. Now,
Sir,
yes,
in the second point,
yeah.
in the third line, what have you written?
Work done by the battery such that we stop.
Oh, okay.
Sir, is it like voltage is increasing, then the electrons will be repelled, and then the emitter shows a 0 reading?
Mm-mm.
Okay.
Yes, exactly. That's correct. We need to make sure that the incoming electrons do not flow. We need to completely stop them. Okay. So we're increasing the voltage so that at one point the work done by the battery in repelling those electrons is equal to the kinetic energy that they could come in, right? Do you understand this? So we can then define the stopping voltage, and stopping voltage is basically minimum voltage required by regulated power supply to stop fastest moving electrons ejected during photoelectric emission in a photocell in the completing circuit. Okay, please do let me know if you have a question here.
Sir, I have seen in some of the past papers, like they have said negative voltage. It is same as minimum voltage, right?
Negative voltage means that it's basically in the opposite direction of the photoelectrons. That's why.
Is it minimum voltage? We can call it.
Yes, we can call that, obviously. All right, you guys done? Should I go forward now?
No, sir, I'm writing the last part.
Okay.
Done, sir.
Okay. Now this question is the same question that we have just done. So you guys just need to, do this. Nothing really is different about this. Just try to do these questions. I've just given you a lot of these because these come regularly. Like this one is frequency one, and again the three qualities of how do you conclude the conclusion drawn from the graph about the photoelectric effect. Obviously, you're going to talk about how maximum kinetic energy depends on basically the frequency, not the intensity. How a threshold frequency is required to eject electrons, and the electron ejector instantaneous. Anyway, so you guys can do the. If you do not understand any of these, do let me know. Okay. Now, I'm gonna stop here. I'm gonna basically. I want you to practice it a bit. Okay. And when tomorrow, like on Monday, when we meet again, we're gonna finish this, and then I just want you guys to do the questions before coming to the class so that you can discuss it, because everything ahead is very related to this, and if you don't understand this, then there's no point in understanding anything that's coming up. Okay, so I will see you then. If you have anything else to ask, please let me know.
Sir, excuse me, sir.
Yes.
Sir, have you said the nodes of electromagnetic induction, EMF?
Yes, I have. The notes are there.
Like, I could not see it in group.
Which notes are you talking about?
The separate one for the Faraday's and the Lenz law that we did in.
The one we did in class, right?
Yes, right.
You're saying they're not in the drive?
Sorry, I can't find it. Like, I think it's my mistake about.
You can't find the file in the drive. It is there, electromagnetic induction. Here it is.
Okay.
Okay, try again. Maybe refresh it. All right. So I will see you then.
I have a question, but it's not really related to physics, is it? I have a question about Pakistan in general.